For those that are live, I just want to confirm you can hear me okay. Can you comment or send me a direct message? Great. Okay, well, let's get started. My name is Natzem, and I'm a second-year PhD student with the Lima College of Optical Sciences. And today, I'm going to take you on an adventure to learn about Schlieren imaging. I'm going to get started with a video and do some live narration as we go. So first, let's get the screen going. Okay, so let's get started. Schlieren Photography was developed in order to look at density variations in fluids. So for example, you can think if you're looking out onto a desert road and you kind of see this like sort of ripply effect happening on the road. That's due to the density variations from the heat transfer of the ground to the air. And so those density variations become visible when you use Schlieren imaging. So let's just go over the basics of kind of how the setup works. This is a very flexible type of setup. So there are many other ways. My cat. There are many other ways that you can accomplish Schlieren imaging, but this is kind of one of the most basic types of setups that you can do. So first you have your point source over on the left side, and it's not necessarily at the focal plane. It can be really far away from the lens, and then the lens bends the light back towards the camera, and here's your camera optics. And so normally the point that you're imaging would come to this point over here. But if you have an object that is transparent, you may not necessarily be able to see it, like air, and there's some density variation. There's going to be what is called refraction. So when light comes into contact with a medium that has a different index of refraction, there's bending that occurs. You can kind of think about this from a cup that has water in it with a pencil, and I got a message. Okay, sorry. You can kind of think of a cup and a pencil. So if you are looking at the water line, you'll see that the pencil kind of looks like it has a sharp bend, and that's what we call refraction. It's just light bending. So you can imagine when you have hotter air or colder air, the light will bend differently through the object. So instead of it going to the ideal point here for imaging, the light will take a different path, and there's a razor here that will block some of that deviated path of the object, and so then that light necessarily won't make it to your camera, and so that allows you to see the contrast variations in fluid. So let's move forward. We're going to go through our setup a little bit. So here we have our camera, and we have a razor, and we have a parabolic mirror with a focal length. In our setup, it's a 48-inch focal length mirror. And so we have to place the mirror away from the light source about 96 inches. And so we have our light source, it expands, it moves towards our mirror, and then it comes to focus at the razor, and then the camera is focused at the razor or at the mirror, and then you'll only see the light that corresponds to the density variations at your camera detector. So let's go through our setup, our physical setup here. Oops. Okay, so we'll start off with the detector over here. I think that's what I point to, or the light source here, and then our detector. And so we have light that travels out to a diffuser, and then it travels out to a horizontal slit. And here's a close-up of the light source, the diffuser, and then here's the horizontal slit. And we'll go over alignment in a little bit if you want to try this at home. And then the light travels back to the razor blade, and then the light continues on to the detector. Okay, so here's a close-up. This is just like some garage blade, garage blade razor. And then the detector, if you wanted to do this at home, it could be a DSLR camera. I haven't personally tried it with a cell phone camera, but I presume it could work with a cell phone camera as well. You just have to mess with the exposure settings. Okay, and over downstream of the setup, so over here to the right of us is where our light source and camera are. Over here is our parabolic mirror with a 48-inch focal length. And these are just clamps that kind of hold it in place. And on the back side, we have adjustments, the left knob and the bottom knob. The bottom knob allows us to tip kind of forward and backwards, and the left knob allows us to tip side to side. And this helps for alignment. Oops. So here we can kind of see a full panorama of the experiment. And then we can see what our detector is seeing here. And there's a few adjustments we can make, like exposure time and frame rate. And these kind of help with making the density variations of the fluid more apparent. So the next thing we're going to talk about is alignment. And what I'm going to do is I'm going to show kind of like a bright image of what I'm looking at, and then I'm going to turn off the light and then show you what the light beam is supposed to look like. So on the right here, we have our source, diffuser, and my face is in the way, diffuser, and then our horizontal slit. So here's me illuminating the field, and then I'm going to turn off the lights and put a piece of paper to kind of show you what the slit looks like as we travel downstream. And then when we come into contact at the mirror, so this is again with illuminated scene, and I'm going to turn off the lights and show you what the beam looks like when it approaches the parabolic mirror. Okay, and then I'm going to show you what the light beam looks like when it travels back to the razor blade. So first I'll show it coming to focus at the razor blade, and then the light continuing to propagate all the way to our detector. So there's the light coming through, coming to a tight focus right at the razor blade. And you'll kind of see that about half of the beam is at the razor and the other half is above the razor. And then it propagates down to our detector and then comes back to focus. Okay, so here we're looking at the Schlieren image of our detector, and this is a soldering iron. And then I blow on the soldering tip, and you can kind of see the disturbance in the disturbance in the air. Not here, but just a little bit ago. And then here we're showing alcohol vapor. So it's a little bit harder to see, but you can almost see that, the vapor, when it evaporates, is cooler. So the air kind of moves downwards as opposed to when there's heat and the air moves upwards. And this is, in line with the thing that you always hear, which is heat rises, cold falls. That's how currents are created. And then in the next Schlieren image, we're going to be looking at acetone vapor. So the bottle will come up, and then you can see this one, the evaporation rate is much higher, and you can see that apparent because the stream is much more easy to visualize. In this Schlieren image, it was just a spray bottle of Expo cleaning solution, and I had to slow it down a lot to even see a little bit. And this one, I'll let you guys guess a little bit of what you might think it is. At first glance, you might think it's a candle, but this is actually just a light, the same light source actually that we're using in our setup. And so you can notice that obviously there's heat coming from the source itself, but then if you look at the body of the light source, here it's not as visible, but if you kind of focus around here when I play it, you can see heat rolling off of the body. And then this is heat coming off of my hand. And so you can see how the air density changes as I, create a bundle of heat in my hand and then open it. And then that there is a little bit, I was very lightly blowing into the place where the Schlieren imaging is done, and you can see that it's the stream is really apparent. Of the stream of air is really apparent. And so, of course, oops, let me show that again. Okay, so that's my hand, and then move forward a little bit. Still my hand. Okay, here comes the breath of air. And then finally, here's a blow dryer. You can see that it's much more turbulent air streams. Okay, so now I'm gonna kind of go over a Schlieren setup that you can do at home. And all it requires is a cell phone with a light source, and then a piece of aluminum foil that kind of covers up the LED from your phone. And if you don't have a phone that has an LED light source, you can, maybe use a flashlight and then again do the foil trick. And all I did was take a small toothpick and I perforated a tiny hole that is maybe a few hairs thick. So it's a very tiny hole, but it's still very bright. And that's all you need. And so you place this light source pretty far away so that by the time it makes it over to your lens, it almost looks like a flat it almost looks like a flat wavefront coming into the lens. And so from the lens, you place your camera behind there, and then you focus accordingly to fill the detector image. And so I'll show you what that looks like as we zoom in. And so here I have a candle lit, and I can just show you the screen, but this is the view from the actual camera itself. So here I'm lighting a match and then turning on a candle. And this, the candle is pretty close to the magnifying glass here. And then as you move outwards a little bit, you can see the density variations more clearly. And then I move it out further, and again, you can see it more clearly. And this is I didn't think I actually finished explaining everything. So it's just a light source with a phone camera with some aluminum foil, a hole poked inside, and then a magnifying glass. So, the larger the magnifying glass, the better. That way you can kind of get a wider field to view. And then the thing that I haven't tried, I have a DSLR camera here, and I'm not assuming everyone has a DSLR camera at home, but this might also work with your cell phone. I haven't personally tried it, but y'all are welcome to give this a go. And again, there's many other Schlieren type of setups that you can find online and do these little tricks with. And here I only showed flame just because that one becomes really apparent. For things that are slightly less, that vary slightly less in temperature variation, it's actually going to be harder to see those things. So because this is pretty hot, it's easy to see. But if the temperature gradient is not as extreme as between a candle and ambient air, you might not be able to see things. So this is a good setup to just demonstrate the principle. And if you think you really like what you're doing, you can try this at home with other setups that cost a little bit more money. For example, like the one I showed you in our lab. Okay, and so that concludes the video. And I'm back online here. So at this point, I'm open to any questions people might have about Schlieren imaging, or about optics, or about school. Anything goes. Okay, if there are no questions yet, there is a really great video that was made that is always a good reminder right now for us, to wear our masks. And so the imaging technique, they used Schlieren imaging to demonstrate the importance of wearing masks. And so I'll share my screen here. And it's a really well done video, so I'm not even going to try and replicate it. So this is just standard breathing. You know, you're talking to somebody, and you know, that's how the particulates, you know, the small particulates in your mouth are spreading through the air. And so what they show here are just various different masks. Let me see where. So here they show a cloth mask, which is pretty good. It stops quite a bit of the air. And here we go. This is the comparison that I wanted to show. So you can see, even though masks do help, there are more appropriate masks than others when you're wearing them. And so, you know, wearing them correctly is also important. So I thought it's really, you know, really neat. This is a good reason of, you know, to study sciences, to help inform public policy. And I think more than ever now, it's really apparent that more science needs to direct policy quite a bit more in order to, you know, really get through this. Okay. So if there's no questions in the next minute, I'll wrap this up. Okay, well, I don't know if that was a minute, but thank you all for joining me. And yeah, I hope you guys found this exciting, and maybe we'll try building this system at home. Yeah, thank you all again for joining, and you know, we'll see what we explore next time. And if there's anything that you have questions, you can still write in the comment box, and then one of us will come answer it later. Okay, thanks.